Okay, hi everyone, welcome to this video on the history of the periodic table. So I'm just going to talk you through how the atom has changed over time because of new experimental data or new scientists finding out different things. Therefore, our opinion and our knowledge of the atom has changed. So there's just certain models that you need to know of, and the first one is J.J. Thomson's model. So you might have heard of this. It's called the plum pudding model. So what J.J. Thomson said was that the atom was a circular shape like that, and this pudding was positively charged. So think of it, instead of a plum pudding model, you could think of it as a chocolate chip cookie. So the cookie itself is positively charged, and inside this cookie there were negative chocolate chips. So that's what he thought the atom looked like. So negative plums or negative chocolate chips, however you want to remember it. So this is the plum pudding model. Positive charge everywhere, and then negatively charged parts just dotted around. Okay, so that's the plum pudding model. But then somebody else called Ernest Rutherford came along and did an experiment called the gold foil experiment. So what he did was he shot a beam of alpha particles, so just very tiny particles, shot a beam of those at a gold foil, piece of gold foil, which contained gold atoms. Okay, so these beams hit the atom. So if I just draw an atom for you here. So hit the atom, and some of the particles actually bounced back. They reflected back. So they must have hit something in the centre of the atom and reflected back. But majority of these alpha particles he found went straight through. Sometimes they hit something else that was in the atom and deflected different ways. So what he concluded was there must be something in the centre, which we know today as being the nucleus. And then because the alpha particles, majority of them went straight through, the atom must be majority empty space. So Rutherford basically disproved Thomson's plum pudding model because Thomson said there was lots of electrons scattered around, the whole thing was positive, whereas Rutherford actually found that the atom is majority empty space. So that's why today we know it as Bohr's nuclear model. Bohr's nuclear model, where we've got a central nucleus like that, which contains protons and neutrons, and then the electrons are in shells or orbitals around the central nucleus. So these are the electrons, nucleus with protons and neutrons, and these are our orbitals. So carrying on from this then, with Bohr's nuclear model, let's have a look at how we can fill out the shells for different elements. So this is called the electronic structure, or it's called the 288 rule. So what you need to do is you need a periodic table. So I've got one here. Let's focus on, how about we try fluorine. So you've got the mass number at the top there, you've got the atomic number at the bottom. The bottom number tells you how many electrons are present in that atom. So for fluorine, we've got 9. So for the 288 rule, what you have to do is just put in a nucleus like that, and you're going to draw the shells where your electrons will fit in. So fluorine, we know, looking at the period, oh, I spelled that wrong. Fluorine has 9 electrons. So according to the 288 rule, in the first shell closest to the nucleus, it can only have a maximum of 2 electrons. Once it's hit that 2, we then go into the second shell, so you've got to draw a second one. Remember, we're trying to get to 9 in total, so we've already got 2. The second shell can only hold a maximum of 8. It can't have any more. It can have less, but it can't have any more. So 2, 3, 4, 5, 6, 7, 8, 9. So in total now, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons, which is correct for fluorine. So we don't need to go into the third shell because that's it, fluorine's done, it's got its 9 electrons. But let's try one that has more electrons. Let's try something like, why don't we try magnesium? Oh, actually, no, let's go with chlorine. Okay, so there's my nucleus. Draw my first shell. It's got 2. It can only have 2 in its first shell. Remember, we're trying to get to 17. So because I've hit that maximum, I now go into the second shell. So I'm still trying to get to 17. So I've already got 2, 3, 4, 5, 6, 7, 8, 9, 10. I've got 8 in this second shell now. I can't get any more in, so I've got to go to the third shell. So I've got to 10, I still need 7 more. So 1, 2, 3, 4, 5, 6, 7. And that's it. That is the electronic structure for chlorine. Okay, right. So let's have a look at the periodic table. So someone called Mendeleev put this table together. And what he did was he grouped elements with similar properties together. So groups go downwards. So the columns. So this is group 1, group 2. We miss out this block in the middle because this is the transition metal block. It's not a group. We just skip that one. 3, group 4, group 5, group 6, group 7, and group 0 or group 8. Either is fine. Coming across, we call these periods, but don't forget helium and hydrogen because even though it's not a full row, that's still period 1. So period 1, period 2, period 3, period 4, period 5, period 6, and so on. So what Mendeleev did, he actually ordered the elements via atomic mass. So if I just write Mendeleev, ordered the periodic table via atomic mass. He also left gaps in the periodic table because he had a feeling that some elements had not yet been discovered. So he left gaps so that in the future, when they were discovered, they could fill into certain areas. And he was actually correct. We have found those elements now that he predicted would be found one day, and they do have similar properties to those in the groups. So it was really important. It's quite incredible that he left these gaps, and it turns out that he was correct. So left gaps so that elements which had not been discovered yet would fit in. And then lastly, like I said, grouped elements with similar properties. So similar properties meaning metals or non-metals, do they conduct electricity, do they not? Do they react with water in a similar way? Do they react with oxygen in a similar way? That's what we call properties. Okay, lastly, let's just quickly look back at the periodic table. So on this side here, we have our metals, and then on this side over here we have our non-metals. So it's just important to know which side of the table are metals and which side are non-metals. So let's just have a look at some properties of metals and non-metals. We'll compare them. So I'll put metals over here, non-metals over here. So some properties of metals then. So they are shiny. Not all, on average, metals tend to be shiny. Not all of them. There are some that don't really fit the pattern, but generally we can say metals are shiny. They're strong, malleable, just meaning they can be bent or hammered into different shapes. They're good conductors of electricity and heat. And they have high boiling and melting points. Okay, so non-metals tend to have a dull look about them. They're not shiny like metals. We can say that they're brittle, so that they break easily. They aren't always solids at room temperature. And they don't generally conduct electricity or heat. Okay, so you can see some pretty clear differences there between metals and non-metals. Okay, and that concludes our video on the history of the periodic table. I'll see you in the next one. Bye.